All right, so we're going to start looking at compound events. Okay, so compound events, we're basically breaking down into two sort of different situations. Sometimes we're going to have mutually exclusive events, and sometimes we'll have mutually inclusive events. Okay, so what does that mean? Two events are mutually exclusive if they have no outcomes in common or if they can't both happen at the same time. Okay, so when you flip a coin, you either get heads or tails. It's not possible to get both at the same time. Okay, if you roll a regular six-sided die, you are going to get a one, a two, a three, four, a five, or a six. You can't get like a two and a three as your answer. Okay, so those are mutually exclusive versus taking an English class and a math class. Those are not mutually exclusive because you could be in both, right? You could take math and English at the same, at the same time, meaning in the same year, right? So since you can do both, it's not mutually exclusive. So those would be considered mutually inclusive. Okay. If two events are exclusive, then we say that they are disjoint from one another. In some situations, you have to break into disjoint events in order to analyze the probability of it happening. Okay. So let's look at these guys. So we have two people selected from a group of 7 men and 5 women. Find the probability that either both of them are men or both of them are women. Okay. So when we look at this one, we're going to have to split this into two distinct cases. One where both are men, one where both are women. There's no overlap in those two. Like it's not possible for both people to be men and also for both people to be women, right? Given the parameters of this problem. So we're going to have to break this into two separate events. Okay. So when we look at the ways to get what we want versus the possible outcomes. So what we want, right? And I'm going to set up my fraction here. Okay. So when we set up what we want, there are two possible outcomes, right? First, they could both be men. Okay. If they're both men, then I'm going to have two slots, right? Where there's 7 men, so 7 times 6. Okay, and the order in which they're selected does not matter, so I'm going to divide that by 2 factorial. Okay, if they're both women, right, then 2 slots where I've got 5 options and then 4 options. And again, the order doesn't matter, so I'm going to divide by 2 factorial. All right, now for this particular problem, the total number of outcomes is the same for both of these situations, right? So when you're setting this up, what you can do is we can just say, let me add these two things together. And then for the denominator for my total, I'll just go ahead and do 2 slots, 7 men and 5 women. That would be 11 people, 12 people. So 12 people and then 11 divided by 2 factorial. Okay, so because they both have the same total number of possibilities, we can just use the same denominator for both of them. If it was a situation where, like if they asked us like, how many ways could you choose 2 men or choose 3 women, then we would have to maybe break it to separate denominators. But for this one, we're good with what we have. So 7 times 6 divided by 2 factorial, which is just 2. And then plus 5 times 4 divided by 2 factorial, which is just 2. So that's 31 on the top. And on the bottom, it's 12 times 11 divided by 2 factorial, which is just 2. So our probability is 31 over 66. So 31 out of 66 is about 4.6. Let's see. So 0.46, and it'll be 9.7. So if I round that to the nearest tenth, that would be 47.0% chance. Okay. All right. So then from there, the second one, now we want a situation where at least one of them is a man. Okay. So this is a situation where we'd have to break it into cases because you could have just one man or you could have 2 men, right? So whenever you get a problem like this, it's always worth stopping to think, would a complement make more sense here? Okay. So if our probability we're looking for at least one is a man, the complement of that is that they're both women, right? So yeah, for this one, it probably would actually be faster to use a complement. But since I'm trying to illustrate how you deal with compound events, I'm not going to do that. Okay. So what I'm going to look at here is I'm going to figure out, okay, well, how many different ways can we do this? So set up my fraction here, right? The number of ways to get what we want. Okay, we want at least one man. So we would have one man, or it could be both of them being men. Okay, if just one of them is a man, then you have 7 options for the first person, and then the other one would have to be a woman, so it would be 5 options there. No need to divide by any factorials because those are mutually exclusive events, right? They are separate from one another. Okay, these two, I've got 7 options for the first person, 6 for the second one, but this one I would have to divide by 2 factorial because they're being pulled from the same category. Okay, so we've kind of been dealing with mutually exclusive things for a while. Right, but then our total, 12 people total, right, times 11 divided by 2 factorial because the order does not matter. All right, so calculating this out. So I got 7 times 5, and then plus, I'm adding to that, 7 times 6 divided by 2, or 2 factorial. So that is 56. All right, and then our denominator is still going to be the same as the last one, 66. Right, we figured that out above. So this works out to, let's see, 84.8%. And there we go. Okay, so that's not too bad. All right, so now let's talk about mutually inclusive events because these ones are a little bit different. These guys, there's no overlap between the two of them, so we don't have to worry about it. Okay, but once we start looking at this mutually inclusive stuff, this is where we're going to have to think back to kind of like our Venn diagram-y stuff. I know it's been a while, but we're going to think back to some of that and use that to sort of help us out. So events are considered mutually inclusive if it's possible for both to happen at the same time, like wearing red and white. You could do both at the same time. Okay, picking a club or picking a 7 from a deck of cards, there is a 7 of clubs, so it's possible to do both. Okay, and then here what we have is this inclusion-exclusion principle that says that when you want to find the union of 2 sets, so when you want to find out how many there are total, you can add set A plus set B and then subtract the overlap between them. So let's come back to that in just a second. We'll illustrate it with the Venn diagram. Okay, so this one we got 200 students, 40 take English, 50 take math, 10 take both, right? So if I make my Venn diagram, okay, so 200 students, here's my English circle, here's my math circle. Okay, I know that jumping to the end, 10 of them take both, so I can put that there. So if 40 of them take English, that's 30, and if 50 of them take math, that's 40. Okay, and then from there, this would be a total of, let's see, 40, 80. So that leaves 120 people who don't take either English or math, which seems unlikely. Okay, so then from here, we could figure out our probabilities. So the probability that somebody takes English, there's 40 people who take English, right? So it would be 40 out of 200, right, which is 20%. Probability that somebody takes math would be 50, right? So 50 out of 200, which works out to 25%. Okay, the probability that somebody takes English and math, that would be the people who take both. So that would be 10 out of 200, which is 5%. And the probability that somebody takes English or math, when it says English or math, there is an understood assumption that you are also allowing for both. Okay, so when it just says the probability that somebody takes English or math or both is understood to be part of that problem. So there's 30 and 10 and 40, so that's a total of 80 people out of the 200, which is 40%. So 40% of them take English or math. Okay, so let's jump back up to this inclusion-exclusion principle, okay? So the inclusion-exclusion principle applies when you're answering this question, okay? You want to know, taking English or math is basically asking you, what are the 2 circles when you put them together? What's the union of the 2 circles, right? So the shortcut way to find this one is that you add together the sum of the two circles and then subtract the overlap. Okay, so like it told us originally that there were 40 people who took English and 50 people who took math, right? So what the inclusion exclusion principle says is it says if you take the 40 and you add the 50, then the people in this 10 group got counted twice. Remember talking about this? So those 10 people got counted twice. They were part of both the 40 and the 50. So we're going to subtract the both section, and that's going to tell us how many people there were total. Okay, so this is the inclusion exclusion principle. So we're taking set A and adding to it set B, and then we're subtracting what the union of those two sets is. I'm sorry, the intersection of those two sets. And that gives us the union of them. Okay, so this one we drew a Venn diagram and it wasn't a big deal. Now, this guy down here, we got a remote jungle, we got probability of getting malaria, the probability of getting measles, and the probability of getting both. Okay, we want to know what the probability is of a child contracting malaria or measles. And again, there's an understood or both there. Okay, it's not going to say or both. You just have to understand that that's part of the problem. Okay, so we could set up a Venn diagram, right, where we would say, okay, well, here's this total and here's this total, and then, okay, we got the both, so we know the both section, and then subtract, right? But the shortcut way of doing it is we use the inclusion exclusion principle. You add together the total probability of getting malaria and the total probability of getting measles, and then subtract from that the overlap between the two. So I'm going to do 0.45 plus 0.65. Notice that's more than 100%, right? Which can't happen, okay? Because we double counted that middle section. So when I subtract that double counted section, we get 0.9. So there's a 90% chance that you would get one or the other, okay? All right, so that is what's going on with this inclusion exclusion principle. Okay, you could have also made a Venn diagram that would totally work. It's just a little bit faster if you can use the inclusion exclusion principle. Okay, so if the events are mutually exclusive, there's no possibility of overlap, you just break it into cases. Okay, if they're mutually inclusive, then you add together the two overall probabilities and subtract from it the overlap of the both section.